Hello everyone, I am Balaji Rao. Welcome to BR Max class. In last class, we completed second exercise of matrices chapter. In this class, we are going to learn theory related to third exercise. We will learn the definition of transpose of a matrix. We will learn the definition of symmetric, skew symmetric matrix. These three definitions, and we will learn properties of transpose of a matrix, and we will learn what is the general pattern of a symmetric matrix, general pattern of a skew symmetric matrix, and one important theorem is there. Every square matrix can be expressed as sum of symmetric and skew symmetric matrix. All the theory part related to third exercise we are going to complete in this video. Okay, so this theory is important. If you understand the theory well, then exercise problems we can do very easily. Now see this definition, transpose of a matrix. What is the definition of transpose of a matrix? If A is a matrix, what matrix it is? Square matrix, rectangular matrix, what matrix? It may be any matrix. If A is a matrix of order m by n, I consider a matrix of order m by n. If A is a matrix of order m by n, then how you will get transpose of matrix A, right? Then transpose of A is obtained. Transpose of A is obtained by interchanging its rows and columns. Okay, so this is important. Transpose of A is obtained by interchanging its rows and columns. Interchanging rows and columns. Here confusion will be there. We need to interchange rows as well as columns. Actually, we'll interchange. Let's see one example. See here what the definition is. If A is any matrix, it may be square matrix or rectangular matrix, whatever it may be. A is a matrix of order m by n, then transpose of A is obtained by interchanging its rows and columns. What is the order of A transpose? All those things I'll give as a note points. First, we'll try to understand how to calculate transpose of a matrix. And one more thing, transpose of matrix A is denoted by transpose of matrix A. Transpose of matrix A is denoted by, how it is denoted? It is denoted by A dash, or some books they'll write like this also, A power T. Transpose of a matrix is denoted by A dash or A power T. Now I'll take one example. I'll calculate its transpose, then we'll discuss properties and all, right? I'll take an example here. I'll take matrix A like this. Matrix A is 1, 2, 3, 4, 5, 6. Okay, I taken a matrix like this. Now I want to write its transpose of this matrix. Transpose of a matrix is denoted by A power T or A dash. You can write in any way. In textbook, most of the time we will see like this, A dash. A dash means transpose of matrix A. Transpose of matrix A is obtained. How you will get? By interchanging its rows and columns. Interchanging rows and columns. That means interchanging rows into columns and columns into rows. Here, little tricky thing is there in this definition. So, very simple thing is, what I'll do, I'll take the first row here. I'll write it as a first column. Okay. First row, you write it as a first column. Okay. First row, you write it as a first column. What you will get? 1, 2, 3. Okay. Now, you take the second row, write it as a second column here. Okay, write it as a second column, 4, 5, 6. Okay, right. Now, this is matrix A. Its transpose is like this. You observe actually what I did. I taken row and converted into column. Right? Interchanging its rows and columns. Transpose of a matrix is obtained by interchanging its rows and columns. That means we interchanged rows into columns, columns into rows. Right? You see here, I just taken the first row, written it as a first column, taken the second row, written it as a second column. Now you can observe here, I just taken row, converted into column, right? Now you observe this thing also already happened. You see here, this is the first column now. You can observe it as a first row here. Okay. You observe here, this is the second column. You can observe it as a second row here. In what way I'll calculate A transpose? I taken matrix A, first row, written it as a first column. Next, I taken second row, written it as a second column. I interchanged rows into columns. Automatically, the columns are also interchanged into rows. This way, we will calculate transpose of a matrix. It's very easy, very easy. I'll take one more example to understand the things more clearly. I'll take one more example. Suppose the matrix A is like this: A, B, C, D. This is 2 by 2 matrix. Okay. How to calculate its transpose? How to calculate its transpose? Just interchanging its rows into columns. You just interchange its rows into columns. You take first row, write it as a first column. You take second row, write it as a second column. Okay. You take first row. First row is what? AB. Write it as a first column. What you will get? You will get like this, AB. Now, you take the second row, write it as a second column. Okay. Now, whatever you will get, that is known as a transpose of matrix A. Actually, I taken row interchanged into columns. When you do like this, columns also interchanged into rows. Look here, this is the column, this is interchanged into row. I hope you are understanding the definition of transpose of a matrix. See, transpose of A is obtained by interchanging its rows and columns. Got it? Right. Now, you learn the definition of transpose of a matrix. And transpose of a matrix A is denoted by A dash or A transpose. Transpose of a matrix B is denoted by B dash or B power T, like this. And you can observe here, what is the order of the matrix A? In this, order of the matrix A is 2 rows, 3 columns. You please observe. This is the matrix A. This is the matrix A of order 2 by 3. You can observe its transpose. Its transpose is a matrix of order 3 by 2. You see, A is a matrix of order 2 by 3. A transpose is a matrix of order 3 by 2. Right? So, if A is a matrix of order 2 by 3, A transpose is of order 3 by 2. If A is a matrix of order m by n, if A is a matrix of order m by n, then what about A transpose? A transpose is a matrix of order n by m. Okay. And you can see here, this is the matrix of order 2 by 2. Its transpose is also of order 2 by 2. I hope you are understanding. I just want to write this note point. Note we'll write here as a note. If A is of order m by n, then A dash is of order, what is the order? A dash is of order n by m. So these are the things you need to know about transpose of a matrix. What is transpose of a matrix? If A is a matrix of order m by n, then transpose of A is obtained by interchanging its rows and columns. You do not confuse here, rows and columns both are there. While writing its transpose, we will just take a row and write it as a column. That's it. We will take rows and write it as a column. Obviously, columns will interchange into rows. That happens automatically. Okay. Right. So, now one more important thing is there. Properties of transpose of a matrix. This is important. You must know what are the properties of transpose of a matrix. Right. 1 minute. What are the properties of transpose of a matrix? Right. First property. A transpose whole transpose equal to A. A transpose whole transpose equal to A. This property can be verified easily with an example. Suppose if I take A equal to, just 1 minute. I'll take an example. A equal to 1, 2, 3, 4, 5, 6. Write its transpose please. A transpose, you take first row, write it as a first column. You take second row, write it as a second column. Okay. Now I will calculate A transpose whole transpose. That means I will write A transpose whole transpose. That means transpose of A dash. Okay. How to get this A dash whole dash? Very simple. In this matrix, first row is there, na? You write it as a first column. Okay. In this matrix, second row is there, na? You write it as a second column. Third row, you write it as a third column. Okay. Now you can observe the matrix A and A dash whole dash both are same. So it can be verified easily that the property A transpose whole transpose equal to A. Okay. So A dash whole dash equal to A. And second important property is A plus B whole transpose can be written as A transpose plus B transpose. There is no proof for these things. You can easily verify with an example. Okay, A plus B whole transpose can be written as A transpose plus B transpose. This property works good. Now third property, A minus B whole transpose. I said one important theorem is there. Every square matrix can be expressed as sum of symmetric and skew symmetric matrix. There we will use these properties. So it is important you need to know these properties. A plus B whole transpose is A transpose plus B transpose. In the same way, A minus B whole transpose is A transpose minus B transpose. Transpose can be written as power T or just simple dash also we can write. Okay. Next, fourth property, AB whole transpose. AB whole transpose. AB whole transpose can be written as B transpose into A transpose. In other words, this can be written like this: AB whole transpose equal to B transpose into B transpose into A transpose, right? Okay. And last property, fifth property, KA. You know K is scalar, A is any matrix. KA whole transpose can be written as K into A transpose. So these things we can easily verify with an example. These are the properties you need to memorize. Till now what we learned? We learned about transpose of a matrix. What is the definition of a transpose of a matrix? And we discussed some examples how to write transpose of a matrix. And we learned that if A is a matrix of order m by n, A transpose is a matrix of order n by m. And we learned the properties of transpose of a matrix. Okay. Now, very important, symmetric matrix and skew symmetric matrix. What is symmetric matrix? Okay, symmetric. 1 minute. Yes. Symmetric matrix. What is symmetric matrix? What is symmetric matrix? What is symmetric matrix definition? Definition, you need to start like this: a square matrix. This is important. It is a square matrix. A square matrix is said to be a square matrix A. A square matrix A is said to be symmetric matrix. Is said to be symmetric. Symmetric matrix if A transpose equal to A. If A transpose equal to A, then the matrix A is called symmetric matrix. If A transpose equal to A, then the matrix square matrix A is called symmetric matrix. In this definition, it is a square matrix. It is important that you need to know that symmetric matrix is a square matrix. Symmetric matrix is a square matrix. What is the definition of symmetric matrix? A square matrix A is said to be symmetric if A transpose equal to A. Can we find an example that A transpose is A? Yes. I'll write you the general pattern here so that with this general pattern you can give thousands of examples related to symmetric matrix. Okay. Now I'll name this as A. See what way to write this symmetric matrix general pattern. Diagonal elements you write as per your wish. Like I'll write ABC. Diagonal elements you can write any three real numbers. Any three real numbers, minus 1, 2, 3, 0, 1, 1 crore, like that. You diagonal elements you write any three, right? ABC. Now this order is there. Now please observe this order. This order here, the elements will be there. Non-diagonal elements in a square matrix, non-diagonal elements. For those elements you follow this order: P, Q, R. Look here, P, Q, R. Please observe this pattern. P, Q, R. 1 minute. Right. Observe this pattern. P, Q, R, P, Q, R. This is a square matrix. If I do its transpose, definitely I'll get A only. If you want, we'll check now. Right. We'll write its transpose. How to calculate its transpose? Just interchanging first row into first column. Right. Here first row is there. Na? You write it as a first column. Write it as a first column. What you will get? A, P, Q. What I did, I taken this first row APQ, written it as a first column. Now I will take second row. You write here it as a second column. What is this? PBR. PBR. Now you observe this third row. You write it as a third column. Q, Q, R, C. You write it as a third column. Third row we written it as a third column. You can observe here APQ, APQ, PBR, PBR, QRC, QRC. These two matrices are equal here. What happened? Therefore, A transpose equal to A transpose and A both are same you got. Right? Therefore, what we can say here? We can say that therefore, whatever the matrix I written A is a symmetric matrix. I hope you understand the definition of symmetric matrix, right? General pattern of symmetric matrix also you learned. With this, you can give so many examples. For example, I'll take another example here, example 1. What I said, to give example for symmetric matrix, diagonal elements as per your wish, 1, 2, minus 3, I'll write. You can write diagonal elements, any 3 real numbers. Any 3 real numbers you can write. Whatever the non-diagonal elements are there, for that you follow this order, PQR, PQR, right? So what I'll do here, I'll 2 or else 4, 5, 6. If I write like this, 4, 5, 6. What elements you will write here? You write the same element. Suppose here minus 4 is there, here also minus 4. Suppose here minus 6 is there, here also minus 6. What is this? It is a symmetric matrix. If you want, you can check. I given general pattern here. Now this is the general pattern of symmetric matrix. Once you know general pattern of symmetric matrix, thousands of examples you can give for symmetric matrix. What is the definition of symmetric matrix? A square matrix A is said to be symmetric matrix. A square matrix A is said to be symmetric matrix if A transpose equal to A, right? Now you learn the definition of symmetric matrix. Now let's see what is the definition of skew symmetric matrix. Okay, skew symmetric matrix, we'll write it. Skew symmetric matrix. Skew symmetric matrix. What is the definition of skew symmetric matrix? A square matrix A is said to be skew symmetric. I'll take this only, I think it is possible. Let's check. Yes, it is possible to take. A square matrix A is said to be skew symmetric. 1 minute please. Okay, a square matrix A is said to be skew symmetric if A transpose equal to minus A. Skew symmetric. Skew. Okay, 1 minute please. I think instead of this we can write directly also. Okay, a square matrix A is said to be skew symmetric. A square matrix A is said to be skew symmetric matrix if A transpose equal to minus A. Right? The definition is similar. Symmetric matrix, skew symmetric matrix, it is easy. When we say a square matrix A is symmetric when A transpose equal to A. When we say a square matrix is skew symmetric when A transpose equal to minus A. When A transpose equal to minus A, we say that the square matrix A is skew symmetric matrix. Now, general pattern of skew symmetric matrix. Once you know general pattern of skew symmetric matrix, thousands of examples you can give. Okay, right. Okay, first I taken a square matrix. Skew symmetric matrix, all diagonal elements must be 0. To give an example of a skew symmetric matrix, first thing you must fill all diagonal elements with 0. All diagonal elements 0. Like a symmetric matrix, what you written? You can write, you see here, you can write any three real numbers. Diagonal elements you can write any three real numbers while writing the example of symmetric matrix. For skew symmetric matrix, all the diagonal elements must be 0. Must be 0 for skew symmetric matrix. Next, you follow this P, Q, R. As if I suppose that P, Q, R are positive. If P, Q, R are positive, you write its negative numbers. Minus P, minus Q, minus R. This matrix 100% skew symmetric matrix. If you want, you can check. What I'll do here, I'll calculate minus A. Look here, I'll calculate minus A. Here matrix A is there, na? Matrix A is there, na? From this I'll calculate minus A. How to get minus A? Minus A is nothing but minus 1 into A, right? To get minus A, each element of this matrix A, you multiply with minus 1. Okay, so what you will get? Minus 1 into 0, 0. Minus 1 into minus P is P. Minus 1 into minus Q is Q. Minus P, 0, R, minus Q, minus R, 0, right? This is minus A. I just multiplied each element of A with minus 1. I got minus A. This is minus A. Now what I'll do, I'll calculate its transpose. A transpose. Calculate A transpose. Calculate A transpose. How to calculate A transpose? You take first row. You write here it as a first column. Okay. 0, minus P, minus Q. I written first row as first column. Okay. Now take the second row. Write it as a second column. Yes. P, 0, minus R. Second row as second column. Now third row as third column. Okay. Q, R, O. Okay. You can observe here, this is transpose of A. Na? This matrix and this matrix both are same. A transpose and minus A. You can observe 0 PQ, 0 PQ, minus P, 0 R, minus P, 0 R, minus Q, minus R, 0, minus Q, minus R, 0. What you identified here? You can easily say that this is nothing but minus A. So definitely, what is this? This is the example for skew symmetric matrix. I hope you are all understanding what I am trying to say. While giving example of a skew symmetric matrix, you consider this point, all diagonal elements are 0. I'll give one more example. If you ask me to give one example, first what I'll do, I'll write all diagonal elements 0. Okay. Now, whatever, if suppose minus 2, 3, I written like this, PQR. Please observe, these are PQR. Exactly opposite sign numbers I'll write. Here minus 1 is there, na? I'll write plus 1. Plus 2 is there, na? Minus 2. Plus 3 is there, na? Minus 3 I'll write. Definitely, this is a skew symmetric matrix. If you have any doubt, you can check. I hope you are understanding. So till now, what we learned in this class, we learned the definition of transpose of a matrix. We learned what are the properties of transpose of a matrix, and we learned the definition of symmetric matrix. What is the general pattern of symmetric matrix? And we learned the definition of skew symmetric matrix and general pattern of skew symmetric matrix. Now, very important theorem. Every square matrix can be expressed as sum of symmetric and skew symmetric matrix. We will see the proof of this theorem now. What is this theorem statement? Every square matrix can be expressed as sum, SUM sum, not SOME sum of symmetric and skew symmetric matrices. I am going to prove this result in this class. First, I'll consider a square matrix. I considered a matrix A. Let A is a square matrix. Now, I want to prove that this square matrix is expressed as sum of symmetric and skew symmetric matrices. What I'll do, I'll consider A plus A dash. Now, I am trying to prove that A plus A dash is symmetric. Symmetric matrix. When we say A is symmetric, if A transpose equal to A, then we say that A is symmetric. If B transpose equal to B, then we say that B is symmetric. If C transpose equal to C, then we say that C is symmetric. When we say A plus A dash is symmetric, when we say A plus A dash is symmetric, when A plus A dash whole dash is A plus A dash, A plus A dash whole dash is A plus A dash, then we say that A plus A dash is symmetric. So what I'll do, I'll calculate A plus A dash whole dash. Okay, we know this property. A plus B whole transpose can be written as A transpose plus B transpose. Here A plus A dash whole dash, this can be written as A dash plus A dash whole dash. As per this property, this can be written like this. Okay, that equal to A dash plus A dash whole dash. In properties of transpose of a matrix, we know that A dash whole dash equal to A. So here A dash whole dash is A. With respect to addition of matrices, commutative law holds good. That means with respect to addition, A plus B is same as B plus A. Here this is also addition of two matrices. So A dash plus A can be written as A plus A dash. So finally what I'll conclude, what I proved here, I considered A plus A dash whole dash and I got that equal to A plus A dash. I hope you are understanding. When A plus A dash whole dash is A plus A dash, then what I can say? I can say that A plus A dash is symmetric. So here I proved that A plus A dash is symmetric. Here we need to know some knowledge regarding to symmetric matrix. This is the general pattern of symmetric matrix. You observe this matrix. If you transpose this, again you will get the same matrix. What I am trying to say, this is the example for symmetric matrix. What I will do, when I multiply this matrix with a scalar, what I will get? That is also symmetric matrix. You can observe this. What I did, I multiplied each element of this matrix with K. Now I got this matrix. You can observe, you transpose this matrix, again you will get the same matrix. What I am trying to say, when a matrix is symmetric, if you multiply that matrix with a scalar K, then whatever you will get, that is also symmetric. So here, what I can conclude, when A plus A dash is symmetric matrix, some scalar into A plus A dash is also symmetric. Here, I will consider that scalar as half into A plus A dash. When we know A plus A dash is symmetric, I can easily conclude that half into A plus A dash is also symmetric. Okay. What I am trying to prove? I am trying to prove that every square matrix can be expressed as sum of symmetric and skew symmetric matrix. I considered a matrix A and I proved that half into A plus A dash is symmetric. Now what I will do? I will prove that A minus A dash is skew symmetric. I am trying to prove that A minus A dash is skew symmetric. You see here, when A dash equal to minus A, then we say that A is skew symmetric. When B dash equal to minus B, then we say that B is skew symmetric. Like that, when I am able to prove that A minus A dash whole dash equal to minus of A minus A dash, then I can say that A minus A dash is skew symmetric. So what I will do, to prove A minus A dash is skew symmetric, I will consider A minus A dash whole dash. Okay. We know from the transpose of a matrix properties, A minus B whole dash. A minus B whole dash can be written as A dash minus B dash. Okay. So this can be written as A dash minus A dash whole dash. That equal to A dash minus A dash whole dash is A. Okay. That equal to, what I can do here, I'll take minus common. You observe, whatever the expression is there, that can be written as, I am taking minus common, A minus A dash. It can be understood easily. When I multiply with minus, you will get minus A. Look here, minus A. Minus of minus plus A dash. So what happened here? I proved that A minus A dash whole dash equal to minus of A minus A dash. This tells you that A minus A dash is skew symmetric. Here you need to know some information related to skew symmetric matrix. What is the general pattern of skew symmetric matrix? You know that this is the general pattern of skew symmetric matrix of order 3 by 3. All diagonal elements are 0. If you take A, B, C, if A, B, C all three are positive, then here all three negative numbers we will take. This is the general pattern of skew symmetric matrix. If I multiply with a scalar k, whatever I'll get, that is also skew symmetric matrix. What I am trying to say here, when A minus A dash is skew symmetric, when I multiply this with a scalar, whatever the matrix I'll get, that is also skew symmetric. So here, half into A minus A dash is also skew symmetric. Okay, you observe here what I got. I got that half into A plus A dash is symmetric. I'll consider it as equation 1. Now you look this, what I got here, I got that half into A minus A dash is skew symmetric. What I am trying to prove, I am trying to prove that this matrix A is sum of symmetric and skew symmetric matrix. Now what I'll do, I'll consider this expression and this expression, I'll add both. Okay, see here, I considered this expression and this expression, now I am adding both. You can observe here, I can take 1 by 2 common. If I take 1 by 2 common, what you will get in the first expression? You will get A plus A dash plus, what is remaining here? A minus A dash. You can observe this, plus A dash minus A dash will become 0 matrix. So that equal to half into A plus A is 2A. So you will get 2A. This 2 will get cancelled. So what you got? You got A. So finally, what is the conclusion? Therefore, A, this is the square matrix, is expressed as half into A plus A dash. What is half into A plus A dash? You observe equation 1, that is symmetric. Sum of, see sum, this is addition, sum of symmetric and skew symmetric. What is half into A minus A dash? Half into A minus A dash is skew symmetric. So what happened? Here the square matrix A is expressed as sum of, see here, sum of symmetric and skew symmetric matrices. So hence we proved the theorem. I hope you understand this class. If you like this video, please drop a like. If you are not yet subscribed to my channel, please subscribe now and share this video with your friends. Thanks for watching this video. Have a great day. Bye bye.